Let us understand green hydrogen. Green hydrogen is hydrogen gas, H2, produced using renewable energy sources, such as solar, wind, or hydroelectric power. This process is also known as green hydrogen production or renewable hydrogen production. There are different types of hydrogen gas classifications named after the colors as per the method of the process of production. What are the colors of hydrogen? Gray hydrogen, the most common form of hydrogen available today, is made from natural gas, typically methane. In a process known as steam methane reformation, SMR, methane and steam react together in a high temperature, high pressure catalytic reactor, and hydrogen is produced. Carbon dioxide is a pollutant resulting from the steam methane reformation process, making gray hydrogen the least sustainable form of hydrogen available today. Blue hydrogen is produced in much the same manner as gray hydrogen, but the emissions generated from SMR are captured and stored underground in a process known as carbon capture and storage, CCS. While blue hydrogen is a lower carbon option than gray hydrogen, it is still associated with consequences deriving from the use of fossil fuels, such as the release of methane into the atmosphere. Green hydrogen refers to a 100% clean solution. Green hydrogen is produced using renewable energy sources like solar and wind. Today, less than 1% of total annual hydrogen production is green, but this is expected to grow as the infrastructure needed to create it is expanded and production costs continue to fall. Other color designations for hydrogen also exist, such as pink, produced using nuclear energy, black, brown, produced using coal or lignite, and white, naturally occurring. These colors are more like labels or classifications, rather than actual colors of the hydrogen gas itself. How is green hydrogen produced? Unlike gray hydrogen, green hydrogen is fully renewable in both its source material and its energy supply. For source material, green hydrogen today is typically generated from water through a process known as electrolysis, which uses an electric current to split water into its component molecules of hydrogen and oxygen. This is done using a device called an electrolyzer, which utilizes a cathode and an anode, positively and negatively charged electrodes. This process produces only oxygen, or steam, as a byproduct. As for energy supply, to qualify as green hydrogen, the source of electricity used for electrolysis must derive from renewable power, such as wind or solar energy. There are three main kinds of electrolyzers: alkaline, proton exchange membrane, PEM, and solid oxide. These vary in the nature of the electrolyte material used. Alkaline electrolyzers utilize an aqueous solution with an alkaline-like salt to enable electrical conductivity, while PEM electrolyzers use a solid polymer membrane electrolyte. Solid oxide electrolyzers use solid ceramic material as the electrolyte, which enables them to operate at higher electrical efficiency and much higher temperatures. This permits the use of steam and external heat as energy sources rather than relying on electricity. Thus, solid oxide electrolysis enables significantly lower cost of operations, since heat is typically less expensive and is sometimes naturally produced as a byproduct of certain industrial processes. Green hydrogen is considered a clean and sustainable energy carrier because, during production, green hydrogen does not release CO2 or other greenhouse gases, unlike traditional hydrogen production methods that rely on fossil fuels. Green hydrogen production utilizes renewable energy sources, reducing dependence on fossil fuels and mitigating climate change. Hydrogen can be stored and used as an energy carrier, enabling the storage of excess renewable energy for later use. Green hydrogen has the potential to play a significant role in the transition to a low-carbon economy, but its production costs are currently higher than traditional hydrogen production methods. However, as renewable energy costs continue to decline, the cost of green hydrogen production is expected to decrease, making it more competitive. The green hydrogen production process involves the following steps. Step 1. Renewable energy generation. Solar panels or wind turbines generate electricity from renewable energy sources. The electricity is fed into the power grid or used directly for electrolysis. Step 2. Electrolysis. Water, H2O, is fed into an electrolyzer, which uses electricity to split the water molecules into hydrogen, H2, and oxygen, O2. The electrolyzer consists of an anode and a cathode, separated by an electrolyte. Step 3. Hydrogen production. At the cathode, hydrogen ions H+ are reduced to form hydrogen gas H2. At the anode, oxygen gas O2 is produced as a byproduct. Step 4. Gas separation. The hydrogen gas is separated from the oxygen gas using a gas separator. The gas separator can be a membrane or a pressure swing adsorption (PSA) system. Step 5. Hydrogen purification. The hydrogen gas is purified to remove impurities such as oxygen, nitrogen, and water vapor. The purification process can involve techniques such as pressure swing adsorption (PSA), cryogenic distillation, or membrane separation. Step 6. Hydrogen compression and storage. The purified hydrogen gas is compressed to high pressure, typically 350 to 700 bar, for storage. The compressed hydrogen can be stored in tanks, cylinders, or underground caverns. Step 7. Hydrogen transportation. The compressed hydrogen is transported to the point of use, which can be a fuel cell electric vehicle, a power generation plant, or an industrial process. The transportation can be done using trucks, trailers, or pipelines. Step 8. Hydrogen utilization. The hydrogen is used as a fuel or feedstock for various applications, such as fuel cell electric vehicles, power generation, industrial processes, e.g., chemical synthesis, steel production, residential heating and cooking. Here are some of the pros and cons of green hydrogen. Pros. Zero greenhouse gas emissions. Green hydrogen production does not emit greenhouse gases, making it a clean and sustainable energy carrier. Renewable energy source. Green hydrogen is produced using renewable energy sources, reducing dependence on fossil fuels. Energy storage. Green hydrogen can be used as a form of energy storage, enabling the storage of excess renewable energy for later use. Improved air quality. Green hydrogen can help improve air quality by reducing emissions from fossil fuels. Enhanced energy security. Green hydrogen can enhance energy security by reducing dependence on imported fossil fuels. Diversified energy mix. Green hydrogen can contribute to a diversified energy mix, reducing reliance on a single energy source. Job creation. The green hydrogen industry is expected to create new job opportunities in production, transportation, and storage. Cons. High production costs. Green hydrogen production costs are currently higher than traditional hydrogen production methods. Energy efficiency. Green hydrogen production requires a significant amount of energy, which can lead to energy efficiency concerns. Storage and transportation challenges. Green hydrogen requires specialized storage and transportation infrastructure, which can be expensive and logistically challenging. Scalability. Green hydrogen production needs to be scaled up to meet demand, which can be a significant challenge. Competing with fossil fuels. Green hydrogen needs to compete with fossil fuels on cost and convenience, which can be a challenge. Regulatory framework. The regulatory framework for green hydrogen is still evolving and can be unclear in some regions. Public acceptance. Green hydrogen may face public acceptance challenges due to concerns about safety, cost, and environmental impact.